Hello everyone. Today I will present my electrostatics lab using charged tapes. The purpose is to observe the interactions between charged pieces of Scotch tape. Determine how much excess charge is on one piece of charged clear tape approximately. There are two computational models, a point charge model and a line charge model. The analysis is based on Coulomb's law, electric force, gravitational force, and force equilibrium. The main result is the computational models produce different charge estimates. Coulomb's law. The main principle behind this experiment is Coulomb's law. It describes the electric force between two charged objects. As charge increases, the force increases, and as distance increases, the force decreases. The lower tape creates an electric field. When the upper tape is placed in that field, it experiences an electric force. In this experiment, that electric force pushed the upper tape upward. Gravity pulls the tape downward. When the tape begins to float, the upward electric force and downward gravitational force are approximately balanced. This equilibrium condition is the key idea used in our calculation. We created two strips of tape and quickly separated them to generate charge. Then we slowly moved them closer together until the upper tape floated. The mass of the tape was 0.000145 kilograms, and the separation distance was about 0.02 meters. Using the tape mass, I calculated the gravitational force using F equals mg. Because the tape was floating, I assumed the electric force was approximately equal to the gravitational force. Using Coulomb's law, I estimated the charge to be about 7.95 times 10 to the negative 9th coulombs. Before starting the model, we answered a few conceptual questions. Since the floating tape is not accelerating vertically, the net force in the y direction must be approximately zero. Therefore, the upward electric force balances the downward gravitational force, which allows us to estimate the charge. Next, we justified our main assumption because both tapes were made from the same material and charged in the same way. We assumed they carried approximately the same net charge. We then modeled each tape as a point charge located at its center. Finally, we used a charged plastic pen to determine the sign of the tape's charge. Since the tape was attracted to the pen, we concluded that it likely carried the opposite type of charge. For the first computational model, I used a point charge approximation. I assumed that both tapes had the same charge and that all of the charge was concentrated at the center of each tape. Using the measured tape mass, separation distance, and the E field function from lab 0, I calculated the electric and gravitational forces acting on the floating tape. The results are shown here. This result suggests that the point charge model agrees very closely with the experimental force equilibrium condition. The second computational model, I improved the point charge approximation by distributing the charge along the entire tape. Instead of representing each tape as a single charge, I represented each tape as many small point charges arranged in a line. This line charge model more closely resembles the real physical tape because charge is spread across the tape rather than concentrated at one location. The same experimental values were used, including the tape mass separation distance and charge estimated from part 1. The results are shown here. The line charge model produced a much smaller electric force than the point charge model. When I increased n from 30 to 100, the electric force increased slightly and moved toward a stable value. This happened because increasing n makes the charge distribution more continuous and therefore more realistic. The difference between the two models occurs because charge interaction happen at many different distances in the line charge model. As a result, the point charge model overestimates the electric force while the line charge model provides a more realistic representation of the tape. The two models gave different results because they used different assumptions. The point charge model concentrated all charge at one location, while the line charge model spread the charge across the tape. Possible errors included measurement uncertainty and non-uniform charge distribution. What if? If electrons were positive and protons were negative, the observation would remain the same. Objects with opposite charges would still attract and like charges would still repel. Only the levels would change. Conclusion. In conclusion, this experiment combined measurements and computational models to estimate electric charge. Among the two models, the point charge model matches the experimental observation most closely. Thank you.